So now we're going to try to use our matrix exponential to solve non-homogeneous systems. In Unit 1, Lesson 7, we learned how to solve the linear first-order equation x prime equals a times x plus f of t, where a is a constant, by use of an integrating factor. And the solution, if you recall, was our complementary solution plus our particular solution, which is c e to the at, the solution of the homogeneous equation, plus e to the at times the integral from t0 to t e to the negative as times f of s ds. That might go back a ways, but I think you might recall doing something similar to that. In a similar fashion, the general solution of the system of equations vector x prime equals square matrix A times vector x plus vector f of t is the solution of the complementary equation plus a particular solution, which is our matrix exponential times our constant vector plus our matrix exponential times integral from t0 to t of e to the negative as times f of s ds. So, as our first example, let's find the general solution of the one we already found the matrix exponential for. And so this is that particular one. I should have a prime on that. So, since we've already found our matrix exponential for this matrix, we might be able to pull this one off. So we've got our matrix exponential, and so x equals, remember the solution, matrix exponential times vector of constants plus matrix exponential times the integral of e to the negative of that matrix exponential times our f of s. So let's see how we can pull that off. Here's our matrix exponential times the vector of constants. Matrix exponential times integral from 0 to t of e to the negative at, actually negative e to the negative as in this case, times the cosh s and sinh s, because that's what's on the right side here. So multiplying this out, we get cosh of s times cosh of x minus sinh of x times sinh of x, and you might recall cosh squared x minus sinh squared x is equal to 1. And so multiplying this out, negative sinh times cosh plus cosh times sinh, well, they cancel each other out, so it's 0. So this integration turns out to be a pretty easy one. Integrating this from 0 to t, we just get, of course this is s and this is 0, and s goes from 0 to t, so we wind up with the vector t0. So what does that mean? That means our solution is, this is the xc, this is the xp. And so the xc, if we multiply this out, this is cosh t times c1 plus sinh t times c2, and sinh t times c1 plus cosh t times c2, here's that part, right? And then finally multiplying this out, cosh of t times t plus sinh of t times 0, so it's just t times cosh of t, and then sinh of t times t plus cosh of t times 0, so that's just t sinh t. And so another way of writing that would be c1 times cosh of t sinh of t plus c2 times sinh of t cosh of t plus t times cosh of t sinh of t. And that's the way we actually used our matrix exponential to solve this system of differential equations that was not homogeneous.
A simple job for simple people.
Wasn't all that simple.